quantum physics, things behave in a way that's counterintuitive. I like that. I think it's cool. It really demonstrates God's creativity, that he upholds the universe in a way that's majestic and wonderful, but it's not the way that we would expect.
Welcome to the Creation Today show, where we bring together interviews with experts and solid Bible teaching. Your host, Eric Hovind, affirms the ultimate authority of God's Word, the truth of creation, and why it matters to you.
Well, welcome to the Creation Today show, where we explore the wonders of creation through the lens of science and faith. Today, we're diving into the fascinating world of quantum mechanics. It's a branch of physics that has revolutionized, I think, we're going to find out if it has or not, our understanding of the universe at the most fundamental level. I mean, from the smallest particles all the way to the vast cosmos, quantum mechanics reveals extraordinary complexity and beauty inside of God's creation. Guiding us through this journey, this conversation, we are privileged to have the president and the founder of the Biblical Science Institute. He's an astronomer by training, but has delved into lots and lots of areas since getting his doctoral degree. Ladies and gentlemen, please help me welcome our friend, Dr. Jason Lisle. Dr. Lisle, welcome to the Creation Today show.
Well, thanks. Good to be with you today.
I got to tell you, our last show with you was on logic and critical thinking, and that I got no problem. And now we're talking about quantum mechanics, something that in my mind right now defies logic. And I'm going, you're going to be able to put these two together?
I'll do my best. It's quantum mechanics. It's probably the hardest branch of physics. But I think if we stick to the basics of it, I think I can give people kind of a basic understanding of what's going on without having to get into all the math, because the math is really hard.
Okay. Well, you travel and speak all over. By the way, people can invite Dr. Lisle to speak at their church. I know this is what you do. You run the Biblical Science Institute. You write on a variety of things. And I love your eclectic knowledge of so many things. And knowing that you love astronomy, and here we're kind of going, I don't know, it feels like we're going to the opposite extreme or the opposite spectrum. You like both ends? Is that what it is? You like both extremes?
I think so. Yeah, the really big and the really small. And of course, to do astronomy, you have to know something about quantum physics, because the way we probe the universe involves looking at radiation that's generated by these quantum processes. So one of the first classes I took in grad school was on internal processes. It was basically quantum physics and how that applies to astronomy. So it is something I've studied. It's fascinating. It's weird. It's cool. That's one of the things too, I think, that draws me to both the really big and the really small, is they're weird. They're very different from kind of the normal way we think about things here on Earth and in the kind of scale that we deal with things. Quantum physics, things behave in a way that's counterintuitive. I like that. I think it's cool. It really demonstrates God's creativity, that he upholds the universe in a way that's majestic and wonderful, but it's not the way that we would expect.
Okay, so for me, when you say weird, all I think of is difficult. And it sounds like you like the difficult sciences, and it takes a smart guy to really enjoy the difficult sciences. So I'm going to enjoy learning about the difficult stuff today with you. That's what I'm going to enjoy. Okay, so first of all, I started talking about you traveling and speaking because in my experience, I have found Christians, I don't know, a little bit scared of quantum mechanics because it's at the frontier. What's been your experience on trying to communicate about this, or people's response to, well, I mean, the weird, as you called it?
I find that if we stick to the basics, I found that people love it. Because when I describe the very basics of it, now I'm the kind of guy that, I love the basics, and then I want to go into more details. And I find if I get into too many details, I lose people. So I'm going to try not to do that today. But I think if we stick to the very basics of what quantum physics is, I think you'll find it interesting. I think the people watching will find it very interesting because it is weird. Particles behave at the subatomic level differently than they do at the macroscopic level. And that's what makes quantum mechanics so interesting. Not necessarily difficult. Once you get into math, it gets difficult. But I think the basics of it are just cool. They're counterintuitive. It's like magic. It's like watching a magic show. You're like, how does that work? It's just neat. I wasn't expecting that.
Well, I have heard some of the conclusions of this and some of the conclusions that theoretical physicists and people like this come to sound absurd. And it makes me go, okay, let's bring some clarity to this. And hopefully by the end of this, you can tell us, are there an infinite number of universes? Is Marvel correct that we are in a multiverse, or is Ant-Man and the Wasp Quantum, or whatever the name of that movie was? Is it true that we could get sucked into the quantum level? So hopefully you got to give us real world clarity at some point here, okay, as you teach us about this.
Of course.
Okay.
Yeah, I don't think there's a multiverse. Although I get it. If I were an atheist, I probably would believe in a multiverse, because the idea is that how do you explain the fact that this universe is so well designed for life to exist and to be possible? And see, I as a Christian have an answer to that, because God designed the universe and he upholds it in a consistent way that makes life possible. But secularists, how do you account for the 1 in 10 billion? It's much greater than that. Odds that the laws of physics are just right to make life possible. Their view is, well, there must be an infinite number of universes, and we just happen to be in the one that got lucky, so to speak. That is one of the major reasons why people believe in the multiverse. And so, but I don't. I believe there's just the one universe. Scientifically, the only way we could know about other universes, you can't scientifically, because science can only study observational phenomena. And if there's another universe, by definition, we can't observe it. It's another universe. The only way we could know about it is if God told us, and he hasn't. So I don't have any reason to believe in that. It's
so interesting that you come to that conclusion. And obviously it's because your starting point, by the way, if you haven't seen his book, The Ultimate Proof on Presuppositional Apologetics, it is a must read. By the time you get to either page 40, 41, or 42, I forget which page, but right there is like the ultimate statement. You got to go read the book for that. But you got the right starting point. I watched a video recently that was from an atheist perspective, and they're trying to answer the question, where exactly did the universe come from? And I don't have time, obviously, to show you the whole video. It's like an hour long, but listen to the conclusion of what they said and notice what is missing. Kent, show us that clip.
Hopefully, the theory of everything will open this locked door. Perhaps it will reveal that we were born from a previous incarnation, a universe before our own. Perhaps we will find that we are lost in the multiverse, just one universe of countless others. Or perhaps we will pry open the door to find ourselves staring into an abyss, an aberration born from a random fluctuation, our existence little more than a quantum dream against a backdrop of unending nothingness.
Well, Dr. Lisle, there's their conclusions. Those are the options based on all the theoretical physics and quantum mechanics and things going on in our understanding of science today. You came to a very different conclusion. So take us on a journey and then talk about that conclusion.
Yeah, that's their conclusion's so sad. It's so hopeless. They don't have really answers to anything. The universe just sprang from a quantum fluctuation. Well, that requires a universe in order for that to happen. And so, it just kind of pushes the problem back. Where did that universe come from? You either have to have an infinite regress like that, which doesn't really solve anything, or you need a genuine creator. And because I'm a Christian, I said, well, yeah, there's a creator God. Well, where did he come from? Well, God's eternal. So he doesn't need to have, he doesn't have an origin. So if you're eternal, you can't have an origin. Now, we know our universe can't be eternal because of things like the second law of thermodynamics, which indicates that energy is constantly going from a more usable form to a less usable form. That implies that our universe has finite age. Doesn't tell you what the age is, but it tells you it's finite. It can't be infinite. And so our universe really does require a creator. That's the neat thing about being a biblical creationist. I can start with what the revelation from God that the Bible gives me, and I can make sense of the universe. I can make sense of why it behaves the way that it does. And then by probing the universe, I can learn a little bit more about the way God thinks about certain things. I mean, God's revealed the most important thoughts in his word, in the Bible. That's how we know how to have a right relationship with him. That's the most important thing. But it is fun to explore the universe and the way God upholds it. And that's what we're doing. When we're doing physics, we're exploring the way that God upholds his creation. And I can explain why laws of physics are mathematical. Because math is the way God thinks about numbers. It's God's mind that's controlling the universe. Therefore, the universe will be mathematical. And that really becomes the case when you deal with quantum mechanics. In quantum mechanics, the distinction between physicality and math it kind of gets a little blurry. We talk about scalar particles and vector particles and things like that. The distinction between math and physicality kind of gets a little blurry. I can explain that. The same God that rules over mathematics rules over the physical universe. So I can explain why there are laws of nature, why they work the way that they do, why they're mathematical, and why we're able to discover them, because I'm made in the image of God. God has revealed himself to me. God's made me in his image. And so I have the capacity on a limited level to study and figure out some of the ways that God upholds his universe. So I can make sense of all of that as a Christian.
So I hear that and I go, I know what the secularist is thinking. He's thinking, you must not know about Schrodinger's cat. You must not know where we're at. You must not realize that we can actually have contradictions. And so that's right. Catch us up to speed on why they would say that and then explain that away. Maybe because again, most people probably haven't heard this and haven't taken the time to watch any videos on it, let alone study it like you have. Get us up to speed on quantum mechanics and quantum physics, and then take us away from there.
Yeah, what you're referring to is a specific application of quantum physics. That's the Copenhagen interpretation, which has to do with particles that are unobserved. And it turns out one of the weird aspects of quantum mechanics, quantum physics, is that particles, when they're unobserved, behave a little differently than when we observe them. And that's wild. But if you think about it, it would almost have to be that way, because when we observe something, how do we observe something? I'm here looking at my computer monitor. How am I able to observe that? Because light is hitting the monitor, reflecting off of it, going into my eyes, focusing on my retina, and being converted into electric signals in my brain. But the very act of observing the monitor has to have photons impacting it. Okay, now photons, they're particles of light. They weigh almost nothing, and so they have very little effect on something as massive as my monitor. So when I observe something, I am affecting it, but the effect is tiny. Now imagine if I'm observing a particle, a single particle. When light hits that particle, it's going to affect it, right? And so we tend to think that our observations of the large scale don't really affect them, and they don't very much. But on the quantum scale, anything that you observe, you necessarily affect it. And so that's one of the problems of quantum physics, is that you affect the very thing you're observing, and you have to take that into consideration. Now, the Copenhagen interpretation says that when something is unobserved, you can think of it as being this and that, two contradictory states. That's not really true. It's a way of thinking about something. And so if there's this cat, and the example that Schrodinger himself proposed, if you have a cat in a box and you have a vial of poison and you have a radioactive element that sends out these random particles, and they're designed to trigger the poison and kill the cat, sadly, but you don't know when they're going to happen, because we don't know how to predict radioactive decays, and so you don't know when that particle is going to go out and activate the vial of poison and kill the cat. You don't know, and so the Copenhagen interpretation is, until you look, you can think of the cat as being both dead and alive at the same time until you look. But once you open the box, it'll be one or the other. And but is the cat really dead and alive at the same time? No, it's not. It's because particles sometimes behave like waves until you observe them, and that's the weird thing about quantum that makes it quantum. And maybe what I should do is give a little introduction as to why things behave that way and why quantum is different from the reality that we think of in the large scale. And one way to think about that is to consider say you consider an atom of helium, for example. Let's see if I can get the slide up here. That's an illustration of a helium atom that you can see there. And so you got two protons and two neutrons in the nucleus, and you got two electrons orbiting around it. And you can think of that in some ways like a little solar system, right? Like the planets orbiting the sun. Yeah, that's kind of similar. In this case, there's just two planets, but there you go. And they're orbiting the nucleus in the same way that planets orbit the sun. The force is different. With the sun, it's exerting a gravitational force. Gravity is what causes planets to orbit the sun. They would go in a straight line, except the sun's gravity pulls on them and pulls them into a circular path. Now, with an atom, you've got the protons in the nucleus. They have a positive charge. The electrons have a negative charge. There's attraction there. And so instead of the electrons going in a straight line, they get pulled into a circular path. And so it's like a little solar system. And that's the way they first thought of atoms, like this little solar system. But there's some differences. And one of the main differences, and it's where we get the word quantum from, is that electrons can only orbit at certain distances from the nucleus. And in fact, there's a minimum distance, and they can't orbit any closer than that. It's kind of like, Mercury is the closest planet to the sun, but we could put a satellite in a closer orbit. We could put a satellite at half the distance of Mercury and it would orbit faster. We could put a satellite halfway between that one and the sun and it would orbit even faster and so on. You could do that indefinitely in the solar system. But in an atom, the electrons have a minimum distance and they can't orbit closer than that. They won't. And then the next distance out, and there's the next distance out. The orbits are quantized. They come in certain quantities, and that's where we get the word quantum from, is that the electrons can only orbit at certain distances. That's one of the weird things about quantum physics.
And we know this. This is like, there's not a scale. It's not you can move it out. It's a here or here or here. And those are your choices.
Right. And for that reason, atoms can only absorb energy. When you put energy into an atom, the electrons can absorb that and pop up to a higher level. It'll pop them out from the level of Mercury out to the level of Jupiter. Okay, but only certain energy levels will do that, and that's one of the things that Albert Einstein discovered is the photoelectric effect. That if you shine radiation, if you shine light of energy that's less than the minimum, the electron can't absorb it. So electrons can only orbit at certain distances in the atom, which correspond to an energy level, and not in between those distances. So it's not quite like the solar system. The solar system, you can orbit a planet anywhere. You can put it at a certain distance, it'll orbit there if you give it the right speed. But with an atom, the electrons only orbit at certain distances, certain quantized orbits. And so that's the difference. And we now understand why that is. And so that's what I would get into next then, is why is it that electrons behave that way? And we now know why they do. And it has to do with another weird aspect of quantum physics, is that when you get to particles on the size of atoms or smaller, you find that particles, particularly when you're not looking at them, behave like waves. And when I first heard that, I misunderstood it. I thought that it meant that you have a particle that moves up and down like a wave. That's not what it means. What it means is you have a particle has a specific location in space. If I have a particle that's here, it's here. It's not there or there or there or there. It's right here. I can give an X, Y, and Z, and that's where it's at. A wave is extended in space. Think of throwing a rock in a lake, and the ripple that moves away from it, that's a wave. And it has area. It's here and here and here and here. In some places the wave is high, in some places the wave is low, but it's extended in space. Now, particles, when they're first born, when they're first created, they move like a wave. They spread out in space, and so they occupy multiple positions at the same time because they're like a wave until you look at it. And when you look at it, the particle will be on one of either the high points or the low points of the wave. In fact, the wave is if you square the wave, it's the probability of finding the particle there. So you won't find it where the wave is zero. Now, given that electrons do this as well, electrons act like waves. They're extended in space. They have a wavelength. And the wavelength will depend on their energy. And there's an equation for that shows, the more energy they have, the shorter the wavelength. And so electrons that are orbiting around that atom, they have a high point in the wave and a low point in the wave. And there's only certain distances where when the wave comes back around, if it starts as a high point on the wave and it comes back around, it's a high point again. And so the wave is self-consistent. But if you were to make the electron orbit in between two levels, let's say at this level, there's 5 peaks and then it comes back to a peak again. In the next level, it's 6 peaks and it comes back to a peak again. If you were to try to make the electron orbit in between those two levels, it would be 5.5 peaks. And instead of having a peak here, you'd have a trough and it would cancel itself out.
Oh, wow.
Yeah, because you see, when you add two waves together, if one of them is a peak and one of them is a trough, they cancel and you get nothing.
Yes.
So the electron can't exist in between two levels because its wavelength would cancel out. And so if you know the wavelength of the electron, and there's an equation for that, you can calculate exactly where the distances are that it can orbit, and they're exactly the distances that electrons do orbit in an atom. So that's why electrons only orbit at specific distances. It's because of their wave nature. It's because their wave would cancel itself out if they were in between two of those energy levels. That's why it works.
That's fascinating. So we know this is mathematically, it's been tested, and this has been tested in real world experiments because we can actually see the wavelengths. We can understand that. And how do they measure the wavelengths again? What is the isn't there a word for the part? Maybe I'm thinking of something else in quantum mechanics, but par.
Well, there's the de Broglie wavelength, but that's basically what is the wavelength of this. But how this was discovered, it was actually first discovered with light.
Parsec. What's a parsec? Am I
Well, that's
thinking
an
correct?
astronomical. That's different. That's an astronomical term
I'm
that
getting my
deals
two
with.
worlds
That's
confused.
different.
Okay.
Yeah, that's different. Yeah, a parsec is a unit of distance, about 3.26 light years. But no,
Okay.
in quantum mechanics, the wavelength. This was first discovered with light. And you might know that most people have heard that there was some controversy with light. Is light made up of particles or is it a wave? And that was the standing question for a long time. And then finally somebody demonstrated that it was a wave. And the way they did this was what's called the two slit experiment. If you cut two vertical slits, say in a piece of paper, and you throw particles through it, right? The only particles that can get through are the ones that go through one of the two slits. And so let's say there's a wall behind it. The particles will land in one of two locations on that wall that correspond to where the two slits are. But waves won't do that. If you have waves that pass through that, think of like a wave tank, and you've got just this plane waves going through it, and you have two slits that are about as far apart as the wavelength of those waves. The waves will go through both slits and they'll form two new waves that come through the slits. And these two new waves will interfere with each other because if there's a peak on one wave and a trough on the other, it'll cancel out. And so you'll get places where there are no waves. And you get places where you get a peak on this wave and a peak on that one, and they add, and you get a really high wave there. And so it turns out that instead of getting two spots on the wall where the waves hit, because of the way the waves interfere with each other, you get multiple slits. You think, 5 or 6 or 7 or something like that. You get many places because those are the places where the wave constructively interferes with itself. And we've done experiments with wave tanks where we can demonstrate that. And based on how far apart the places where the waves constructively interfere, and based on the distance between the two slits, you can calculate the wavelength of the waves. Now, with a wave tank, we could see all this. You can see the waves happening. And so we've done experiments to measure that. But the cool thing is you can do it with light too. And this has been done. Now, when I first heard about this, I was a kid when I read about this, and I tried cutting two slits and shining a flashlight through it, and you get two bars. And I'm like, I don't see this effect. That's because the slits have to be comparable to the wavelength of the light. They have to be really small. But this has been done. You can take two microscopically small slits, shine light through it, and instead of getting two bright spots, you get like 7, because those are the places where the light waves go through and interfere with each other and then create these bright patterns. In fact, I think I have an illustration of this. Let me see if I can bring this up. So you have a light source there, and then the red is this wall, and the red has two little slits in it. And you can see the light going through both slits, and then it forms new waves, and they either add or cancel each other out. And the places that are kind of gray on the right are places where the light cancels itself out. So you would see multiple bright spots on your screen when this happens. And so it's really remarkable. But here's where it gets really cool. Because we also know that light behaves like a particle sometimes. And that, again, Einstein's photoelectric effect demonstrated that the light comes in certain quantities. And we can shine light through those slits one particle at a time. So what do you think happens when we shine light through one particle at a time? I mean, the prediction was, well, if light's a particle, it'll either hit neither slit and it's absorbed and you don't see anything, or it'll go through one slit and land on the left, or it'll go through the other slit and land on the right. And so if you do it one particle at a time, you ought to see 2 vertical bars. But that's not what happens. If you shoot light through one particle at a time, it'll go through both slits, interfere with itself, and then land on one of those 7 or so bright, where there would be bright spots. It'll land because it's interfering with itself, and it'll land on one of those slits. So apparently, because you're not looking at it, even though you're shooting light through one particle at a time, it'll behave like a wave, spread out, go through both slits, because a wave is spread out. It can go through both, interfere with itself until it hits the wall, and then it's got to make a decision, because now it's got to be a particle again. And it'll pick one of the spots where the wave is highest. Yeah, let's see if I have this. Yeah, here's the illustration of this. You can see that a little bit above. Yeah. So right
Yeah.
there, I know it's kind of small, but you're shooting particles through. The particles will go through even one at a time, interfere with themselves, and land on one of the bright spots. Isn't that wild?
That is crazy.
Yeah.
And this is the frontier of quantum mechanics and understanding what a particle is, wave or particle, and it's almost like it's both. So, can you
It's a
bring
wave.
clarity to
It's a
that?
wave when you're. But there's no violation because some people say, well, that violates laws of logic. No, it doesn't, because a law of logic says you can't be A and not A at the same time and in the same sense. Particles are never both particles and waves at the same time in the same sense. When you're not looking at it, when it doesn't have to be at a specific location, it'll behave like a wave. When you observe it, it'll behave like a particle. Okay.
That's
So,
amazing.
yeah. So as long as you're not observing, it'll go through both slits and land in one of those 7 bright locations. And here's the really weird thing, because scientists were perplexed by this when this was first discovered. They thought, but which slit did it go through? It's one particle.
You're
How can it go
right.
through both slits, right? And so what they did is they put a detector on one of the slits, and you don't have to do both. You just need a detector on one of them, because if the detector says nothing, then it must have gone through the other slit, right? If you put a detector on one of the slits, it won't do it. It'll
What?
pick one. Yeah, if you put a detector on either one of the slits, it won't generate the pattern of interference. It'll go through one slit or the other and end up in one of the two, either left or right. If you're
See,
watching, if you're
that's
watching,
crazy.
it affects the result. And that's what's cool. And that's what, when you're first exposed to quantum mechanics, you're like, this is weird. This is so cool. But it does make sense. There is a logic to it, because remember the rule. It acts like a wave until you observe it. When you put a detector on one of the slits, you're observing it. And so that forces it to
Wow.
not be a wave anymore. It'll be a particle. And so it'll either go through the left slit or the right slit. And therefore you can't get the interference patterns. It'll either land on the left or on the right. But if you don't observe it, one particle will act like a wave. It'll go through both slits, interfere with itself, and then it has to decide when it hits the screen which one of the 7 or so places it'll land on. So there is a logic to it. It's rigorously logically consistent. It's just weird. It's not what people would expect. And I think that's what makes quantum mechanics very, very cool and very interesting.
Okay, you've studied this out. What does this mean for the creation worldview? Because you're right, and this is where at the beginning of the show, I was like, I meet people who are like, wait, does this disprove God? Does this show us the inconsistency? Does this show us problems?
No problems, no inconsistency. It's rigorously consistent. It's just not what you'd expect. And so it shows us that God's mind is a lot more complex and a lot more. God is brilliant on a level that we can't comprehend. We can't. I mean, we've spent centuries, well, at least a century, studying quantum mechanics. Is probably the newest branch of physics. And it's like a century old now, in terms of really starting to understand how it works. And we're still scratching the basics. There's still stuff we don't understand about quantum mechanics. There's a lot that we do, but it's not the way we would expect. But it's what makes atoms work. That's why you see, if God didn't do it that way, if God didn't have that wave nature, and electrons could orbit at any distance, there would be a tendency for them to lose energy and spiral into the nucleus, and the electrons and protons would destroy themselves. They would form neutrons, and you couldn't have matter. So the existence of
Wow.
matter, and by the way, the properties of all the atoms that exist are determined by these rules. They're determined by the wavelength of the electrons. And so the reason that lead is heavy, and the reason that it conducts electricity, and the reason that helium is a gas at room temperature, and the reason that it's inert, and so on, these are all determined by the wavelengths of the electrons. And so just think about how complex that problem is. You're going to create a universe, and you want to have 90 or so naturally occurring elements that can be combined into molecules, because that's all based on quantum mechanics. And you want this all to be determined on the wavelength of the electrons that orbit the atoms. I can't comprehend the intelligence necessary to put that together. It's totally beyond me. It's totally beyond
And
me.
honestly, that's I guess what comes to my mind is the people that are saying there is no designer, and yet you study the science today, and you're like, we cannot create, let alone understand a lot of what is actually created. God's mind is beyond comprehension. It's way past anything that we have thought or imagined. The Apostle Paul, no, I have not seen nor heard, neither had entered into the heart of man the things that God has prepared. What's next? Oh my goodness, it's going to get apparently even better if the Apostle Paul said we can't even imagine what it's like. Hey, I've got to let social media go, but social media, you need to go and read Dr. Lisle's series. You did an entire series on this on your website, biblicalscienceinstitute.com. And you can see it on the screen right now. You need to go, if you're interested in this, go. I don't know how long you took on this, but there's a lot of data in that series. Just start right at the beginning. Excuse me, start right at the beginning of that series and kick off to understand this. Is that the best way to do it?
Yeah, if you go to our website, click on topics, physics, and then there's the quantum particles series. And it starts with a brief introduction to quantum mechanics, and then it gets into the kinds of particles that God's created, which I also like. It's like a taxonomy. There's certain animals that God made. Well, there's certain particles that God made, and there's certain ones he didn't. And it explores those particles and their properties and why they have those properties. I think it's fascinating. So I hope you'll enjoy that.
And you're studying it from the biblical worldview where you're going, of course, an intelligent designer would know that you need this and this and this and this kind of particle in order to eventually get this, and all to bring him glory. Hey, while you're there, you got a donate button on your website. Make sure you click donate and support Biblical Science Institute. And honestly, just like Creation Today, monthly donation is the best. So just become a monthly supporter so you can keep him on the road, keep him writing his articles and resources and things like that. That is really helping. Dr. Lisle's helped. I can't even imagine how many millions of people understand the truth about concepts so that they can take it to their family and friends and speak truth in an intelligent way to others, which is really his whole point. So it's what he wants to be used to do. So thank you, Dr. Lisle. Just love the work that you're doing. Hey, we're going to continue with our Creation Today partners. If you want to come over to creationtoday.org, you can join the rest of this conversation. Next week, I want to have a conversation about music. I find the numbers and the mathematics of the mind of God, oh my goodness, it also applies to music as well. And so I want to look at that next week with my friend Ben Everson. Until then, go share your faith with somebody who needs to hear it. Thank you guys for joining us.